So now let's just plot some points of let's like a new one. Let's do powers of q. I'm gonna skip powers of p. We did that in class. So let's say 1 minus I. Where's 1 minus I? 1 minus I is right here. So this is q right here. Q squared is 1 minus I times 1 minus I. That's 1 minus 2I minus plus I squared. I squared is -1, so it's just 2I. So it's right here. -2, sorry. -2I. Right, this is q squared right here. Q cubed. We have -2I multiplied by 1 minus I, so it's -2I, right? And so let's see. So we have -2I times 1 minus I, so it's -2I, right? And minus 2, because I squared is -1, right? So it's going to be right here. This is q to the third power. I do q to the fourth power, right? Essentially, so there are two ways to do it. I could take -2I multiplied by 1 minus I, or I could just take -2I and square it, which I think is a little easier. So I'm just going to take -2I and I squared. I'm going to get -4, because -2I squared is going to be 4I squared, which is just -4. Okay, all right. So this is q to the fourth power. Now, I can do q to the eighth. If I square -4, I'm going to get 16. So q to the eighth is right here, the very tip, right? But maybe we should put some intermediate numbers just for funsies. Okay, so maybe I'm gonna cross out these guys, and let's try q to the fifth power. Q to the fifth is q to the fourth times q, so it's -4 plus 4I, right? It's gonna be q to the fifth. I take q to the sixth, right? I can just take q cubed squared, so it is -4 minus 2 times -2 times -2I, so it's like uh plus. Am I doing the right thing? So I have -2. It's like 2 times -2 times -2I, right? And plus, you know what? It's just I'm gonna save myself some anguish, because square of a negative number is the same as square of a positive number. So I'm just squaring 2 plus 2I squared, so it's 4 plus 8I plus 2I squared. So it's 4 minus 4. 2I squared is -4. So I just get 8I. 8I. Okay, good. All right, that's where I expect it to be. It's q to the sixth. Q to the seventh is q to the sixth times 1q, right? So that's not too bad, right? So it's like 8I plus 8. I'm gonna switch it around so it looks like the complex number in standard form, right? This is q to the seventh, and that's q to the eighth. Okay, so if you were to try to follow these guys, it sort of looks like a spiral, someone mentioned. Okay, but I'm gonna do it slightly differently. I'm gonna draw vectors, right? So I'm gonna connect them without an arrow to make my diagram not too cluttered. If I were to connect them to the origin, so imagine that these, yeah, let's turn them into vectors. Why not? Imagine these vectors, right? Notice the pattern here, that whenever you multiply q by itself, what happens? It rotates 45 degrees clockwise and also scales by a factor of square root of 2. If you look at all of these vectors, right, the length of these light segments, right, if you were to calculate them, you would notice that after every multiplication, the length is increased by square root of 2. Okay, that's not a coincidence. It's not a coincidence. We're not going to prove this, but essentially, if you have the magnitude of z times w, where there are two complex numbers, that's the magnitude of z multiplied by magnitude of w. If you take the argument of the product, that's the gives you the sum of the arguments. Okay, so right now it looks a little bit weird, right? I mean, you got some intuition of what's going on from what you're saying, but let's actually go a little bit deeper and understand what this thing means. Okay, because I didn't tell you what the argument is yet, and so let's do that. Um, so let's do this. Okay, so let's say we have two complex numbers, z and w. Okay, so let's say there's a start with complex number z, right? This angle over here, the that z makes with the positive x-axis is called the argument of z. And the length of z from the origin is called the magnitude of z. Okay? So this over here is the argument. And this over here is called the magnitude. Now let's imagine we have another complex. So the other complex number is going to be, let's say, w, right? So something like this, right? And I'm going to multiply w by z. And the result is going to be something over here like this. This is going to be zw. So the magnitudes are going to multiply. So this is magnitude of w, this is magnitude of z. The magnitude of their product is going to be the length of w times the length of z. But the angle is going to be the sum. So this angle over here is argument of z. So w just got rotated. Right? By the argument or the of angle z. So the result over here is that the argument of this new vector is going to be argument of the product is going to be the sum of the two little arguments of it. Okay. And I could prove it to you, but you know, it's going to be kind of annoying. So I could try an example, which is going to be a little bit better. All right. So let's try some easy example. Let's try multiplication by I first. Okay. So let's pick some complex number, any complex number. Let's say 4 plus 5i, something. Okay. That's pretty straightforward. It's complex number 4 plus 5i. Now, if I were to multiply, so it's a z, I take z and multiply by I, I'm going to get 5i times I is going to be negative 5, and 4 times I is 4i. So this number is going to be right here. So this is z, this is I times z. Okay. Notice that the magnitudes of these two numbers are the same. If I were to take the magnitude of z, I'll get square root of 4 squared plus 5 squared. And if I take the magnitude of I times z, I'm going to get minus square root of negative 5 squared plus 4 squared, which is, I'm not going to bother calculating it. I think it's clear to see that those values are the same because negative 5 squared and 5 squared are the same value, right? And also, it looks like this is a right angle. Now, why is this the right angle? If I were to look at the slope, right, of this line, slope is rise over 1, right? So the slope of this line is going to be 5 over 4. And the slope of this line is going to be 4 over negative 5. if you were to look carefully, these two values are negative reciprocals. And if the slopes of lines are negative reciprocals, if you remember from 8th grade, the lines are perpendicular. Okay, so that does it. Okay, so it means that we can conclude multiplication by I is equivalent to 90-degree rotation counterclockwise. And that's it about the origin. And that's it, right? Because there's no scaling. Okay, the magnitude is the same. Okay, so let's try another example. Let's try to multiply by something like 1 plus I. Okay, let's try 1 plus I. Okay, so let's say we have 3 plus 4I, and you multiply it by 1 plus I. So I could graph it here and see what happens, but what I'm going to do is I'm actually going to multiply it out in a weird way, and we'll see what's going on. So 3 plus 4I, so if I multiply 1 plus I, it's 3 plus 4I plus, actually, no, let me make it slightly different. Let me make it 2 plus 3I. Make it 2 plus 3I. So I'm going to be 3 times 2 plus 3I plus 4, 2 plus 3I times I. Okay, so I'm going to draw on the side over here the number 2 plus 3I. Here it is. Here's the complex number 2 plus 3I, which is essentially says go 2 units to the right and go 3 steps up. Okay, let me change that color so it's orange. So it says go 2 to the right and go 3 up. Okay, so 2 plus 3I represents this number in the complex one. Okay, now what I'm going to do is I'm going to take this multiplication and try to express it on the complex plane. So it says take 2 plus 3I and add it to itself 3 times. So scale it by a factor of 3. Okay, I'm just going to draw it very carefully. So 2 plus 3I is this one over here. Ooh. I hope I did not. Yeah, it looks like I overshot myself a little bit. I overestimated myself, but that's okay. I can probably go to a new page. And I think it's going to work out. It's my hope. All right. Okay. So, I just took 2 plus 3I and then multiplied by itself 3 times. So here it is. And now 2 plus 3I times I think we already realized it, right? From this part, that's 2 plus 3I. It's going to be rotated by 90 degrees, right? So this part, 2 plus 3I times I, is 2 plus 3I rotated by 90 degrees. All right, so here it is. 2 plus 3I rotated by 90 degrees. Okay? And it says take it 4 times. So this over here represents 3 times 2 plus 3I plus 4 times 2 plus 3I times I, which is also, incidentally, the same as 3 plus 4I times 2 plus 3I. Now, if you were to do some algebra here, let's try to multiply everything out. So 3 times 2 is 6. I'm going to do it very slowly. 3 times 3I is going to be 9I 4 times 2 is 8i, and 3 times 4 is 12, plus 12i squared. Now I squared is negative, right? So negative 1, so 6 minus 12 is negative 6, and 9 plus 8 is 17. Is that true? Does this look like it's right? So this point is like, if you look at the horizontal distance, looks like it is 6. If we count squares this way, it looks like it is 17. I don't know if it is, but looks like it. 3, 6, 9, 12, 15, 16, 17. Okay? So looks like it works. Okay, so this number is minus 6 minus 79. So if I follow this path, I actually get where I'm supposed to. Okay? So this over here is the result from the multiplication. Okay? Now let's look at what's happening here. So I start off with 2 plus 3i, which is this complex number, which is represented by sum of 2 unit vectors to the right and 3 unit vectors up. Now let's look at this triangle and compare it to this large triangle. Notice that this is exactly the same idea. We have 3 units in one direction and then 4 units at the direction which is perpendicular to the direction we started with. Well, these two triangles are similar, but there's just some sort of scaling. But let's see. So this over here, this angle, this is argument of 2 plus 3i. Am I wrong? No, I am wrong. Yeah, no, I'm right. Or am I wrong? Yeah, no, I'm right. Oh, whoops. I drew a wrong thing here. My mistake. I meant to do something else because I don't know how to count. I meant to draw the other one here. I meant to do something like this. So I meant to do this. I meant to draw 3 plus 4i. Now we're good. Now we're cooking with oil. Okay, so this is 3 plus 4i. Right, so now this triangle over here, 3 plus 4i, is similar to this triangle over here because the ratio of the sides is 3 to 4 in both cases, right? So we start off with this vector 2 plus 3i. And you add it to itself 3 times. So you rotate the 90 degrees and you add that 90-degree rotation 4 times. So essentially this triangle over here is similar to this tiny triangle over here. What is the difference? The difference is that we took the unit vector and scaled it to the length of 2 plus 3i. And we took the, the original vector, right, which points in this direction. And we, instead of starting from the positive x-axis, we actually rotated it first by the argument of 2 plus 3i. So this angle over here is actually argument of 3 plus 4i. And we can't really verify the angle, but we can definitely verify the magnitude. So if I want to verify the magnitude, which is also a bunch of annoying calculations, right? So let's try magnitude of 2 plus 3i. That's square root of 2 squared plus 3 squared. That is square root of 13. What is the magnitude of 3 plus 4i? Now, that's lucky. That's square root of 3 squared plus 4 squared. That's 5. So, sorry, so let's see what happens when I take magnitude of negative 6 plus 17i, their product. Magnitude of negative 6 plus 17i is the square root of negative 6 squared plus 17 squared. 17 squared is 289, and 36 squared is 36. So I have 289 plus 36. which I think is 325. So just on the side here, I take 200. Well, I'm going too fast, so there's no benefit in doing that. So square root of 36 plus 289, right? And when I add, I should get square root of 325, right? And I'm hoping, it's my sincere hope, that this number is 5 times square root of 13. Well, let's see. 325 is divisible by 25, so it's square root of 25, and 25 times 4 is 100, so 25 times 12 is 300. So this is this. Okay, so it does work. So the magnitude of the product is a product of the magnitudes, at least in this case. But actually, it's true in all cases. So I can apply the strategy to any pair of complex numbers, right? And it's gonna work. So this is a visual, kind of like proof, sort of, that when you multiply two complex numbers, the arguments add and the magnitudes multiply. Now, we care about this because when you have two complex numbers, right, essentially, multiplication by a complex number is a transformation. So when you take one complex number and you multiply by another one, you are essentially doing a transformation. Now, we will in a moment see how useful and awesome it is, but now we're gonna stop the video.